I can't believe spring break is next week, but I guess it would be nice to have a little break. Hopefully get caught up if we're a little behind. Okay, so when we met last on Monday, today's Wednesday, we're talking about the Lewis structure model. So we talked about different ways of representing compounds or molecules when you're communicating with other people. I did talk about, let's see, the molecular formula and the empirical formula. So when we scroll down here, we see the 3D representations that shows you how scientists draw or represent molecular structures or formulas. So starting with the left, we have a molecular formula represented this way. We have structural formulas. Now you can see in the molecular formula you're being shown what elements or what atoms are present in the compound. In the structural formula you're being shown the atoms present, but how the atoms or the elements are connected to each other. So you're able to see bonds, right? So here I would say in the structural formula, what is important it is relative positioning and the bonds. What kind of bonds do we have? Do we have single, double, or triple bonds? And then with the ball and stick model, this is a model, right? So models are usually for instruction or for communication. So this is built from this structural formula. Now, the reason why the model bonds are bent versus straight and vertical and horizontal, like we see in the formula, this model here considers the actual positioning in real life. So this is more showing you more of the actual location of atoms. Okay, so in this chapter, we'll be talking about the Lewis structure, which the one on the left is the Lewis structure, or the structure of left is based on Lewis structure. The ball and stick model is based on what we call Vesper model. So the Vesper model is a step up, it's an improvement of the Lewis structure where it shows the actual location of the atoms relative to a central location. In this case, this is our central, showing you how these other four atoms are arranged around the central atom. In the model, oh yeah, space filling model. In the ball and stick model, it once again shows you the bonds. The bonds are shown as sticks and then the atoms are shown in the shape of balls. In the model, this is actually showing you, when I said the actual location of the atom, this is showing you the actual view. So if studying the atoms and they're using a powerful electron microscope like a scanning one, so scanning electron microscope SEM, what they see is this. They don't see the bonds. So the atoms are not, they don't scoot back to show you what's underneath. You don't see the bonds. So the bonds are assumed based on how the atoms behave. Okay? So space filling model is what the atoms actually look like when you're studying them. Once again, the bonds that we see here, the bonds that are shown here, are assumed to be present based on what it takes to break the bond, based on how the atoms are arranged. So they're not necessarily easily seen. When you're drawing the structure, you show them there because that explains the attachment between the different atoms and molecules. Okay, so once again here, you have the space filling model. If you are studying this, this is what you will actually see. But from here, they make the size of the atoms smaller so you can see how they're actually connected. Okay, and then you have the different illustrations of the actual molecules. This is what they look like in the powerful electron microscope. And then once again, you're working backwards to see the number of atoms. Okay, so I'll go back here where I said start here. Once again, our context here is how do you communicate the structure or the elements present in the compound. First one we're going to be looking at is Lewis model. Now for the Lewis model, you can draw the Lewis model for an element or for a compound. So when you're looking at a question, either in your homework or in the exam, when you recognize Lewis model or when you recognize the term Lewis, you want to be aware that Lewis tends to talk about valence electrons from the point of view of dots. As I was learning this as a student, I decided I make up my own stuff to kind of help me see the important stuff I have to remember. I always said as a student, Lewis really liked dots because he represented electrons as dots. Some other people represent electrons as X's or pluses, but he shows electrons as dots. So when we're dealing with bonding, as far as bonding is concerned, bonding involves the sharing or exchange of valence electrons. When atoms are trying to combine with each other, the parts of the atom that gets exchanged in the process of forming the bond is the valence electrons. For that reason, when Lewis is drawing his model, he focuses only on what is changing, which is the valence electrons, not the core electrons, because they, for the most part, remain constant. As far as 1411 and 1412 is concerned, core electrons will remain constant. Okay, so valence electrons is what he focuses on. The other thing I want to mention is the number of valence electrons, I'll abbreviate as VE, is equal to the group number. So if you want a quick way to know the number of valence electrons in an element, look at the positioning. And when I say group number here, we usually use group A. So group A. So if an element is in 1A, it has one valence electron. If it's in 2A, it has two valence electrons, and so on and so forth. Okay? So if you're asked to draw the Lewis model, or if you're asked to pick from an answer choice the Lewis model of an element, you will have the symbol of the element in the middle, and then you will have the valence electrons around shown as dots. Now, the order of drawing these dots around the symbol doesn't really matter. You can start from the left. Let me erase this little dot here. You can start from the left and then up. The way you work it out is you put one dot around the symbol. So top, bottom, left, right. Once again, order doesn't matter. And once you have four dots around the symbol, then you go back and pair it. If you have to put the fifth one, you put it next here, seventh, eighth. Oh, sorry, fifth, sixth, seventh, eighth. All of a sudden, I can't count either. Oh my goodness. Anyway, the Lewis dot structures it illustrates the structural formula of the element or the compound with its valence electrons. So we use the valence electrons to draw that structure. Okay, so down the road we'll be doing the same thing, but we'll be doing this for compounds. For right now, we're practicing this for elements only. Lewis structures focus on valence electrons because chemical bonding involves the transfer or sharing of valence electrons between two or more atoms. The valence electrons are the ones that are being exchanged or shared to form the bonds. Okay, now we're talking about the octet rule. What is the octet rule or the rule of 8? When an atom bonds, they tend to either gain, lose, or share electrons to result in a noble gas-like configuration. I mentioned this earlier. The noble gas is a group of elements, right? That family or group of elements. This is group 8. Okay, or I can say here group 8. So why are elements trying to be like group 8? Group 8 elements group 8 elements tend to be stable and they have lower energy because they're stable. For that reason, when the other atoms bond, now when he's referring to atoms here, they mean the group A atoms. Okay, that's 1A, 2A, all the way to 7A. The rationale, remember that we as humans are trying to understand elements. So it's kind of like if you had a dog, because when I was a student, I was trying to understand where the author was coming from. First, I was just trying to learn the content. Then I realized learning the content wasn't making sense to me because I'm a logical thinker. Things have to make sense for me to really understand them. So I was like, but why is the author writing like this? So imagine, right? You have a dog and your dog has certain unusual behavior, and you're trying to explain the behavior to somebody else who is looking at your dog making the same judgments you're making. And you're saying, well, that's how he behaves. Really? Yeah, when he gets food, he just circles around because he's very happy. Why? That means he's happy. Did the dog tell you he's happy? No, you're making an assumption that he's happy. So as scientists are looking at atoms, and looking at their behavior, their assumption is they're gaining, they're losing, and they're sharing electrons. Why? Because they have a goal. What is their goal? To have a noble gas-like configuration. So scientists assume that the reason why group A atoms behave this way is because they want to be stable. And the way they become stable is by gaining noble gas, which is group A, configuration. Okay? So since the elements in group A are essentially in group A, they call this the octet rule. When the elements in group A, starting from group 1 all the way in group to group 7, gain, lose, or share electrons, we will see that. So we're talking about group 1, A, all the way to group 7. Remember, we're skipping about group B, right? Group 7, A. These elements here, after they become stable, will be surrounded by 8 electrons. Okay? After they gain, lose, or share electrons. So the goal, the target they're looking for is to be surrounded by 8 electrons. That is why this is called the octet rule, the rule of 8. Now remember, the purpose of scientists coming up with rules is for the rest of us who are not performing the same experiments that they are doing to be able to come up with the same conclusions without the experiments, right? So the rules are not 100% perfect. They do have holes in them. There are times where they don't work. So of course, we will talk about exceptions. And the exceptions we'll see, these will be elements that do not fall under the category of octet rule, or they don't follow the octet rule. They do gain, lose, or share electrons, but they don't end up with 8 electrons. Okay. So there we go straight to the exceptions. This is just part of chemistry. With every rule in chemistry, there are exceptions. So once you get you start to expect that, you get over it. For me, when I was a student, I was like, oh, there we go with the exceptions. Why can't they ever just make a rule that's perfect? You know, that was me. Now that I'm a little bit more mature than I was as a student, I'm like, okay, I recognize it's complicated to find a one size fits all rule, right? So there's always going to be exceptions. Okay, exceptions to the octet rule. So we're starting with, these are a group of elements or atoms. Remember, these terms are being used interchangeably, that have what we call expanded octet. What is the expanded octet? What does that mean exactly? The expanded octet just means that they're able to form more than 4 bonds. They're able to be surrounded by more than just 8 electrons. So they are beyond octet. And so there is no dectet rule or anything like that. So we just call them exceptions to the octet rule. So what are these elements? It's told they involve the nonmetal elements located in period 3 and below. Okay, let's see. Do I have a periodic table somewhere here? I just realized again. One needs a periodic table. So let me do this, right? Let me add a page here and then go find my trusted periodic table from my previous chapter. Okay, so give me just a moment as I do this quick detour, because I tend to need periodic tables. In class, I would have one on the wall and I'll walk up to it and I'll refer to it. But y'all are not seeing my wall right now. Okay. Okay. I need to clean this up before I copy it so I don't have a lot of mixed up stuff here. Okay. This should be clean enough. Okay. Please. I hope this works because once you start flipping to a different page, then let's see. Go down one step. Please work. Yay. Okay. There. Okay, so we're being told where to find these elements, right? So they're saying find a non-metal element, okay, located in period 3 and below. So I'm going to find this right here. Period 3 is similar. It's not exactly like, but it's similar to energy level 3. So this is period 1. I'll say here period 1, 2, 3. So find non-metals. Okay, so when I look at this right here, that's this group right here. Okay, because silicon essentially is a metalloid. Remember, aluminum is a metal. This is a metalloid. This is a non-metal all the way to the right. So let me erase these labels right here. So they're referring to this set right here. So what they're trying to say is, if you look at period 3 right here and below, and you find the nonmetals, if these nonmetals are the central atoms, they are able to, not all the time, as needed, they are able to expand their bonding capacity to accommodate many extra elements if that is needed. Okay? Right. So let me try to paraphrase that as we see talk about this. So elements in period 3, such as I had a list right here: phosphorus, sulfur, chlorine, when they are central atoms, are able to expand their bonding capacity to accommodate extra atoms. Okay, so when I was learning this in school, it took me a few tries to really understand this, because at first it was mentioned that, oh, these elements, of course, and below, right, the nonmetals, they're able to bond beyond octet. I'm like, okay, what does beyond octet really mean? And then does this happen all the time? So I assumed that every time you saw a phosphorus, a sulfur, and a chlorine, they were bonding beyond octet. But it's not necessarily all the time. It's only as needed. Only as needed do they actually, and they have to be the central atom. So I view the central atom as a host that is holding or supporting all the surrounding atoms. So they have to be, number one, a central atom. And then the need has to arise. You have to have extra atoms that require, forming more bonds to hold on to the extra atom. If the need is not there, they can still be a central atom and then bond in a regular way. Because it took me a while to realize it's not all the time, right? So for me, yeah, going over this a lot in many different classes made me realize, oh, okay, so it's only as the need arises. Okay, so non-metals period 3 on down in the periodic table follow the octet rule when they're not in the center. Remember, for them to have that expanded octet, they have to be in the center. They have to be the host holding on to other atoms. But if they're not in the center, they don't have to follow the, above and beyond bond formation. They don't have to form expanded octet. So if they are surrounding atoms, they bond normally. If they're central atom and you have too many atoms surrounding them, they will expand to form more bonds. Okay, the center atom is the atom in the molecule that the other atoms individually bond to. So I tend to call the central atom the host. So I'm going to label it here or draw a picture or sketch. A will be my center atom or central atom. Okay, the central atom has a role of bonding to other atoms. So my generic surrounding atoms will be X. So you want to make sure when you're drawing your Lewis structure that the central atom has the ability to bond to many other atoms. For that reason, when we're talking about the rules, we will never pick hydrogen as a central atom because hydrogen can only form one bond. That is not a good central atom. Okay. Now going back to these elements in period 3, when they're the central atom, they can accommodate more than 8 electrons, right? Because they can form more than 4 bonds. And how do they do that? They use empty valence d orbitals that are predicted by quantum theory. Okay, don't worry about understanding this right now. We will focus on this in the next chapter, chapter 5. Okay, either 5 or 6, the other chapter. We will show how those elements, S, P, S, C, L, are able to use the d orbital to expand their bonding. Okay, then we're being told that there are other exceptions to the octet rule. These are elements that bond with less than octet. Okay, they didn't even make the cut. So before I go into this, I want to talk about the periodic table and show you the poster children, or should I say the poster elements for octet rule. And I call this the SNOF group. Okay. SNOF referring to carbon, nitrogen, oxygen, and fluorine, because I have to find a way to refer to them without looking at the periodic table. So I just call them SNOF, like carbon. I mean, KNOF sounded weird, so SNOF, right? So carbon, nitrogen, oxygen, and fluorine, these are the poster children, so to say, for the octet rule, meaning that they tend to obey the octet rule all the time, the rule followers. Okay, so carbon, nitrogen, oxygen, fluorine, these are the octet rule followers. So if you want elements that will behave right according to the octet rule, pick any of these and they obey the rule. They're such compliant elements. For that reason, carbon is the first element, starting from the beginning, right? If you start with hydrogen, atomic number 1, hydrogen, helium, lithium, beryllium, boron, carbon is the first element to obey octet. Okay, what does that mean? That means hydrogen does not obey octet. Helium with atomic number 2 does not obey octet. Lithium doesn't, and beryllium doesn't, and then boron doesn't, because carbon is the first element. Once we get to carbon, that is the first element that obeys octet. It obeys octet, nitrogen obeys octet, oxygen obeys octet, fluorine obeys octet, and then we go on from there. Then when you get to down here, they don't have to all the time. They do it sometimes, they don't sometimes. It gets complicated, right? So if the first, how many? 5 elements, right? Starting from hydrogen to helium to lithium, beryllium, and boron. If they don't obey the octet rule, how do they bond? So we're being told here hydrogen, helium, lithium, beryllium, and boron. These bond with less than 4 bonds. Remember, each bond equal 2 electrons, right? So one bond uses 2 electrons. So when these are done bonding, if they bond with less than 4 bonds, that means they have, so these have less than octet electrons. When they have formed bonds in a compound, they end up having less than octet of electrons. Why? Because they are just not able to form 4 bonds. They're not able to be surrounded by 8 electrons. Well, that's not really the reason. That's the observation. The reason is because they come in with fewer electrons. So they would have to gain, in some cases, 6 electrons to form an octet, and that's not possible. Okay? So without getting too far ahead, here's the thing. When we get to the actual bonding, we'll talk about this. As far as gaining or losing electron is concerned, elements can gain or lose one, two, or three electrons max. At the level that we're learning chemistry, general chemistry, this is the max. Now, once you go into research, research is all about going into places that are not normal, right? Trying out the new, the unfamiliar. So we're not going there. We're sticking with what is common, which is elements can gain or lose one, two, or three electrons max. Since we have this maximum limit, the first five elements can never follow the octet rule. For that reason, they're telling you here hydrogen, lithium, beryllium, boron attain an electronic configuration like that of helium. Helium can only have two valence electrons. So since it has two valence electrons, it's called duet. Now, duet tends to be used in a singing group where you have two people singing together. But yeah, here they mean duet with two electrons. Lithium will have to lose one valence electrons to have a duet of electrons. We'll see that later on. Hydrogen shares or gains one electrons to have a duet. And so they're showing you that these elements here will then be able to bond without getting to octet. This is very important. We'll mention this later on. So though it commonly loses its one electron, hydrogen, when it loses its one electron, becomes H plus. So we'll see this when this actually plays out, depending on what hydrogen is bonding with. So hydrogen is unique because it can gain one electron, it can lose one electron, and it can share its one electron. Okay? So scientists tend to argue, well, hydrogen has behaviors of both metals and nonmetals, right? But anyway, interesting. We won't get into that right now. Once we get into the bonding, we'll talk about that. Beryllium loses two electrons to become beryllium 2 plus. And then boron loses three electrons to become boron 3 plus. Okay. Remember, boron is a metal, beryllium is a metal, right? Based on its position. If you look right here, where was the zigzag? Did I remove this? Yeah. Beryllium metal. Boron, yeah. Boron can lose and it can also share electrons, right? Because it's a metalloid, so it has the behavior of both. Okay, now we're going to be using Lewis symbols here to predict the chemical formula for the ionic compound. The Lewis symbol, for the most part, if you've had this in high school, it is used to predict the formula for molecular compounds. But for right now, we're looking at ionic compounds. So ionic compounds, remember, these are compounds formed between metal and nonmetal about 95% of the time. Okay, there are exceptions. There's some ions that are not metallic, but 95% of the time, ionic compounds are formed between metals and nonmetals. So here we're going to be using our Lewis symbols to predict the structure. So I'm going to add a page here as we talk about the structure. When calcium and chloride want to form a compound, how do they bond? Okay, so we're going to use Lewis dot symbols. Okay, symbols. Okay, so as we're using this, remember the overall goal is to surround atoms with 8 electrons. I'll say here, if possible, right? Because remember, there's some that can't do it, and if they can't do it, they just can't do it. So what are we going to be doing though? So I'm going to talk about things that we are allowed to do. We are able to use as many elements as possible to I say make neutral compound. I'm trying to remember the rules in my head since I'm kind of making this up. Okay. The one thing they haven't mentioned here yet, as we're talking about ionic compounds, are right here. All compounds are neutral. I know there's so many rules in chemistry. I understand. If you're feeling that way, this is a normal feeling. Okay. I understand. All compounds are neutrally charged. So they are neutral, meaning no charge. So if we're dealing with ionic compounds and we're going to be making charged ions because ions are charged, then we are allowed to use as many elements as possible because our goal is also to make a neutral compound. Anytime you try to make a compound, the compound has to be neutral. Okay? So, what are we doing again? Yeah, using calcium and chloride to make a neutral compound. In the process, we're going to be making sure that each of them, if possible, is surrounded by 8 electrons. Okay, let's start. Calcium. Calcium is in group, let's see. Calcium is right here, right? This is group 2A. This is 1A, 2A. Let me erase all this because by now we've moved beyond here. 3A, 4A, 5A, 6A, 7A, 8A. And then chlorine is in group 7A, right? So while I'm here, let me go ahead and write this the lowest symbol. Calcium, chlorine. Calcium 2A, I put 2 dots. This is group 2A. Chlorine group 7A, I put 7 dots. Up, left, bottom, right. That's 4, 5, 6, 7. Okay, so I analyze this. Now, before we do the next steps here, the other thing we have to remember, I'll say here that metals lose their valence electrons when forming bonds. Okay, this is true regardless of the type of bonds. It's just the nature of metals. Remember, metals are very large, and so the nucleus struggles to hold on to those last valence electrons. They're too far away. It's like, you're so far, I can't reach you. It's hard to hold on to the last electrons. So metals, due to their size, struggle to hold on to the last electrons, the valence electrons. So they easily lose their valence electrons when they're forming bonds. That means the future of calcium is to lose 2 electrons. These are its valence electrons, right? Remember, calcium is to the left of the zigzag right here. So calcium is a metal. Chlorine is a nonmetal being here. What is the nature of the nonmetal? Nonmetals gain electrons when possible to have a surrounding electrons. Of course, on the elemental symbol, right? So in my elemental symbol, when I look at chlorine right now, it's like 1, 2, 3, 4, 5, 6, 7. Ooh, it just needs 1 to get to 8, right? So the future we see for chlorine is it will gain 1 electron, okay? Based on these definitions or these recalling of the properties of metals and nonmetals. Okay, so let's go down here and see what actually happens as we work this out. Calcium, as we predicted, will lose 2 electrons. Then calcium has now lost 2 electrons. We write calcium after it loses 2 electrons as 2 positive. Okay, this one here shows you that calcium has lost 2 electrons. It produced, which is you have to produce the electrons to lose it. Okay, well, here's the thing though. Didn't I say somewhere here in so many words to be surrounded by 8 electrons? So how is it possible that calcium now has 8 electrons? This is where I was telling you guys earlier that having that Bohr's model kind of helps us with this. Okay, So remember, I'm going to take a step back and show you guys those Bohr model energy level because it makes it easier to show how all of a sudden losing 2 electrons produces 8 electrons. Because it took me a while to get this part in school, and I want to kind of resolve things for you right now. Calcium is in what energy level? So let's go back here. I need to copy the periodic table again. Calcium is right here. Y'all see that, right? So calcium has 20 electrons and it's on 1, 2, 3, 4 energy level, right? 20 electrons. That means calcium, being energy level 4, essentially looks like this. Calcium, as you see, it was an energy level 4. Imagine the simple calcium is where the nucleus is. This is the first energy, second, third, fourth, right? This is N is 1, N is 2, N is 3, N is 4. So, as usual, calcium has how many electrons total? 20. Look at the periodic table. So, the first 2 are on energy level 1. The next 8 are on energy level 2, up, left, down, 2, down, right. Okay, so I've got 4, 5, 6, 7, 8. Now I have placed 10 electrons. I do the same thing for the next energy level. Up, left, bottom, right. That's 4, 5, 6, 7, 8. So now I've placed how many? 18 electrons. That's replaced remaining 2. 1, 2. Okay. So these on energy level 4, these are our valence electrons. They are the ones that got lost here. So once calcium loses the valence electron, the 2, let's show how the loss plays out. I touch this here, boop, they're gone. Oh, let me get rid of that one. So once the calcium has lost 2 valence electron, what is calcium now surrounded by? It used to be surrounded by 2 electrons. Now it's surrounded by how many? 8. 1, 2, 3, 4, 5, 6, 7, 8. So it's like exfoliating. I know it doesn't say that, but I was in school. I was like, oh, now I get it. Like exfoliation, you know? And my teacher's looking at me like, because it's a male teacher, he doesn't exfoliate. He's looking at me like, it's like exfoliating the outer layer. You remove the 2 electrons and the whole energy level, revealing the new skin. I mean, the new energy level that has 8 electrons. He's like, yeah. Anyway, that's how this calcium is now surrounded by 8 electrons. The 8 electrons was always underneath, so they show it like that. Calcium now has 8 electrons around it, and then the charge is plus 2. So essentially, remember, this is consistent with octet. Okay, now what's the story with fluorine? With fluorine, we said fluorine had 1, 2, 3, 4, 5, 6, 7, right? Fluorine was going to gain 1 electron, and when it gains 1 electron, fluorine now has 1, 2, 3, 4, 5, 6, 7. This is the gained electron. This is the gained electron. Okay, here's the thing. Where does fluorine gain its electron from, though? Okay, so this is what happens. Let me reconcile this. Once the 2 electrons get lost here, right, they are taken in by fluorine. The 1 fluorine comes here, takes in that 1 electron. But the way this works, the number of electrons lost must equal the number of electrons gained. So number of electrons lost equal number of electrons gained. Okay, so if 1 fluorine gains the 1 electron, then we need a second fluorine here to gain the other electron. Okay, so you don't have electrons being made just flying around in the air like there's nothing special going on. So the second fluorine comes in to gain the second electron so that now all the electrons that got made by calcium get completely used. So you have this first one here, you have this other one going all the way up down here to our second fluorine there. Okay, Once again, this is a new electron. I should have used a different color. You get the idea, right? So this is what we have here. Now, I have forgotten the charge. I have it, I'll put minus here because it gained one electron, minus here because this gained one electron. Sometimes they use brackets around it so I can do that, I guess, to be consistent. Minus there. Okay. So once everything is said and done, the species we're working with here is now, oops, I clicked the wrong thing. This one here is now this one here, right? After octet, you see how we have the 8 electrons around here? After octet, the same thing happens here. Now we have 8 electrons around this fluorine and the second fluorine, 8 electrons. Okay, now after the transformation, we have our 1 calcium and the 2 fluorides all have octet. So we have our 1 calcium surrounded by these 8 electrons having a charge of 2 plus. And then we have our 2 fluorides, right? Each having a charge of negative. It's like a whole story. And what had happened, each having a charge of negative, right? Now, remember they did this to be stable. So they should be stable, right? And they should not want to react with each other because remember, noble gas elements don't want to react with other people. But here's what happened in the process, though. They got negative charges here, and there's the opposite charge, the positive charge here. So even though they are stable as ions, they attract each other because of what they call electrostatic force of attraction. Anyway, a force of attraction forms a force of attraction, right, due to opposite charges, causes these to get together and they form calcium fluoride, like that. The 1 calcium combines with the 2 fluorines and we get that calcium fluoride. So this is Lewis's version of how bonding happens using the Lewis symbol. Okay, it's like a whole story, starting with the metal, losing electrons, getting an octet as the outer layer where the electrons go away. Then the nonmetal is the responder. The nonmetal gains the lost electrons, also getting its own octet. But in the process, the metal gets a positive charge, the nonmetal gets a negative charge. They're drawn to each other due to force of attraction, and then we get what we call the ionic compound. So just in case you're asked to illustrate this, this is the story you tell, and this is how you illustrate it. Okay? So let me go over here and make sure I haven't skipped over anything. Oh, calcium and chlorine. Oh, I was telling a story with chlorine, right? How did I switch it to fluorine? The concept is the same. I started here with calcium and chlorine, and y'all didn't say anything. It's the same concept. It doesn't really matter what the element is. It's the same. On, I forgot what the central element was. It's the same concept, y'all. Now I'm being hard on myself. They did say chlorine, right? But remember, chlorine and fluorine are in the same family, so it is going to be the same behavior. They're relatives. Oh no, who is this? Hold on. Yeah, this is chlorine. I'll put chlorine right here. It's the same. Nothing is different. Just a symbol. That's it. So this is going to be calcium chloride. Okay. Yeah, that's why I always try to go back to the picture so I can make sure I'm looking at the right thing. Yeah, so they explain this. That's how we get this right here. And this is how we finally write it out. Okay, now they want us to do our own ionic compound for calcium and oxygen. Calcium and oxygen. Okay. Oh, this one here, we're not using Lewis symbol, right? They just said write the formula for the ionic compound that forms between calcium and oxygen. That's just it. Okay. So for this part here, since we're not using Lewis symbols, I'll just to write formula between calcium and oxygen, right? All we're doing here is they didn't say we have to go through Lewis dots. The other way to do this, look at your metal and your nonmetal, right? Calcium is in group 2. So what I'm going to do here is add a page, actually add a page above it, and then bring back that periodic table that was here. Okay, copy this, and then let's see, where am I? Down here, and then see if I can paste. Can I paste this here? Oh, great. Okay, so as I'm working on this part here, calcium and oxygen. See, calcium is in group 2, right? So this is 2A. Oxygen is in 6A. So you got 3, 4, 5, right? These are all A. Please notice, elements in group 2A form a charge of +2. This forms a charge of +1. Group 3A +3. And then 4A doesn't form a charge because we can't form +4 or -4. 5A -3, -2, -1. And then 8A doesn't really form a charge. Okay? So the position of oxygen makes oxygen normally form an oxide of oxygen 2 minus, or oxygen -2. Calcium, based on its positioning, forms an ion, calcium ion, of Ca2+. Since they said go ahead and form a compound, our goal is neutral compound, right? Neutral compound. So if that's our goal, then the question is, how many of each ions is required to make a neutral compound? We have 2 positives here, we have 2 negatives here. It looks like we just need one of each, right, to neutralize the compound formed. So the way we show this here is by the crisscross method. Bring this 2 down here, bring this 2 down here. In the process, the charge is lost, so we get Ca sub 2, O sub 2, and then divide by 2, so we get CaO. And this is just saying to make a neutral compound, you need one of each ion, okay? So 1 calcium ion and 1 oxide is needed to make neutral compound. That is what you're communicating when you look at this compound right here. One of each, 1 calcium ion and 1 oxide ion. Okay, that's it. So that should be our answer right there. I don't need this page anymore. I can delete the page. Oh, and I can delete this one too. Okay, so here they show you the ions based on the group positions. Please notice, I don't know why, there's an error in this. This is supposed to be 2. So all of group 1 elements form an ion of +1. All of group 2 elements form an ion of +2. Then it goes on and on, right? Skip the B block. +3, -3, -2, -1. Make sure you have this somewhere, okay? This list is important to remind you of the elements and the charges. Okay, so right here, I already did all that stuff, so I'm done. I can now move over here. Finally, naming ionic compounds. My goal was to get to the nomenclature part. Okay, so when it comes to naming ionic compounds, what I'm going to do here is, it's hard to kind of go through here, but anyway, I will detour right here because you guys do have that lab you have to work on. I will detour here and try to write as small as I can. We're going to talk about naming compounds in general. So naming compounds. When you're naming compounds, the first thing you have to do is ask yourself, what kind of compound are you trying to make, name, right? So I'll say here, do you have a compound where the first element is a metal? So you want to, so say you're given a compound, let's say you're given X and Y. You judge the first element first. So judge X, judge the first element. Is this a metal or a non-metal? So you have to really know what your metal symbols are and your non-metal symbols are, or have a periodic table close by. Is it a metal or a non-metal? So if your first element is a metal, then as far as this chart I'm about to draw is concerned, you want to go to the left. I'm trying to make this up as I go, right? So bear with me. And then if your first element is a non-metal, you want to go right, okay? Non-metal. Okay, so I'm going to start with the metal part. Now, you judge your first element, and since we're here right now, let's say you judged it as metal. Okay, we're not done. You're not naming it yet. Now, with the metals, there are two options. It can be, let me give an example. Let me give an actual example. Let's say we're working with sodium chloride. Okay, we look at sodium and we say, hey, sodium is a metal. So we said it's a metal. Okay, we're good. We're going left. But there's more than one type of metal. Now that we said it's a metal, is it a group A metal or a group B metal? What do I mean by that? Let's go back to our little handy dandy chart right here. Remember, group A metals, these are the A group metals, like this one here and this section right here. Group B metals will be something in the D block or the F block. So you have to answer that question, right? Is your metal here or here, or is it here and maybe here? Okay, remember these are the A's and these right here are the B's, because the way you name those makes a difference. So you could have, I'll say, group A, or you could have group B. Okay, so I'm going to spend my first the remaining time, but the time I have right now, focusing on group A and group B metals. So here's the thing. If your first element is a metal and you're about to name group A or group B metal, most likely what you're naming here is an ionic compound. So remember, I told you guys I'm building this as I go, so I am going to be modifying a lot as I remember more information. So if your first element is a metal, that means your second one is a non-metal, right? So the compound essentially is, yeah, as I said, I'm going to be making modifications a lot here. It's essentially metal plus non-metal. So we tend to call this in general ionic compound. Okay, now this is the identity of the first element. Over here, I'll say if your first element is a non-metal, then we're dealing with most likely molecular compound. So I'm trying to make this a little shorter as I go here. So non-metal, non-metal. But it all boils down to your identity of the first element. So I'll say here, identify first element. Since the second element tends to be non-metal, that won't help you much. You're trying to figure out what's different about the compound, right? So if you have non-metal, non-metal, you most likely have molecular compound. Molecular compound. Okay? So if you have a group A metal or group B metal, for group A metal, you're going to be naming ionic A compound. Group B metal, I call this ionic B. Okay? So with ionic A, how do you name ionic A? Okay? The short form of this is, once again, I'm going to write here and I'm going to add and erase because I'm building this as we go along. Our example we had right here was sodium chloride. Remember, I mentioned this previously, right? The elements or the metals in group A, which would be example here, sodium. Sodium is in group 1A. Sodium has this characteristic. It has a fixed charge. Okay? It is always +1. Okay, when it forms an ion. So sodium always forms an ion of +1. So sodium always forms sodium ion like that. Because it's in group 1A. Remember, the A metals have fixed charges. So just in case, A metals have fixed charges. Okay, now we're trying to name it. What has all of this got to do with its name? Because it has a fixed charge, imagine you're on the phone talking to somebody saying, hey, can you get me 500 grams of sodium chloride? Oh, okay. Because there's only one sodium ion, right? There's no question about it. And then, of course, the chlorine, this one here, will be named as an anion, so chloride. So when you're naming sodium chloride like this here, the first element will be named as an element. The second part of the formula will be named as an anion. So what I'm writing here is a template for nomenclature. If you have an ionic A compound, the ionic A compound will only have two parts to its name. The first element is named as the element, the regular element name, usually the metal, right? The second part of the formula is named as an anion. Now, the anion usually has the format either STEM-ide or STEM-8, okay? But just remember, the non-metal part, so I'll just say here, second element, it could be, many of them. This is the non-metal part. The first element usually is the metal part, right? Is named as an element. The anion is the non-metal portion. Okay, for ionic B though, because ionic B, the metals have more than one charge, it's not as simple as what we saw with sodium. So let me give you guys an example here. With ionic B, nomenclature is really not that simple. People say, oh, naming, I will figure it out. And then let me just tell you honestly, most people don't do very well in naming because they relax their defenses saying, well, there's no math in this, so it's got to be easy. It's very systematic. Let me tell you something. Those of you going off to organic chemistry, they have organic nomenclature, and it's more complicated than what we're doing right now. Well, is it more? Yeah, it's more complicated than what we're going to be doing right now. Okay, it requires systematic logical thought. Well, there's not a whole lot of logic in naming, but it requires systematic. That's why it's called nomenclature, not just naming, right? You have to follow a system and follow rules as you're naming them. Okay, where was I? Now we're trying to name ionic B compounds. In ionic B compounds, for example, iron. Since you guys took your common ion exam, you recognize that there are two kinds of iron. There's an iron 2 chloride, or I'm going to use chloride as my example. And then there's an iron 3 chloride, right? So let's crisscross this and make a compound. We end up with iron FeCl2. I'm going to crisscross this to make a compound. I end up with FeCl3. Now, once again, imagine you're on the phone. Now, they don't tell you to imagine you're on your phone, but I had to do that to force my mind to connect. I knew what they were communicating. At this point, I begin to know my mind, and I'm like, my mind won't think that's important. So I have to find a way. And the way I found to deal with this is if you're on the phone, okay, still ordering chemicals to somebody in a different country, you're like, hey, Hans, I need to get 500 grams of iron chloride. And because Hans understands that there is more than one type of iron, no pun intended there, he asks you for clarification. Well, which iron do you want? Because I'm looking at the shelf right now and I see two irons. I see iron 2 chloride and I see iron 3 chloride. He can't just assume which one you mean because it's more than one type of iron. And you're like, oh, Hans, my bad. I meant iron 3 chloride. So when it comes to communicating the group B metals, you have to specify the charge for the sake of communication, right? You got to specify the charge. So here in the format, we have the metal as a metal, but this time we specify the charge. So this will be called, I'm going to name only the second one, iron 3. The 3 is written in Roman numerals. So notice that. This is going to be Roman numbers or numerals in parentheses. And then the Cl, the non-metal, anion, chloride. So iron 3 chloride to specify the charge, right? So here, the format of nomenclature is we'll name the first element, the metal, as an element. We will specify the charge, and then we'll name the last part as an anion. Okay, so when you're looking at the names only, you can tell ionic A compounds from ionic B because ionic B had that charge. This is the first, I just say metal, right? Because we're getting better, right? At this. This is going to be the metal, and this part here will be the non-metal. Okay, so it's not that simple. You don't just get to a formula and then provide a name. It's almost like, once again, it's systematic. You're going through a bunch of rules before you provide name. Imagine if humans were named by that, like that. That would be so weird. Let's see, height 5'2", shorty. You don't do that. You're not supposed to do that. No, we have names like Bob and whatever. It's not systematic, right? Even though, like in my culture, when babies are born, they're provided some kind of systematic nomenclature names. It's not this deep. It's not this deep, but in Ghana, that's where I'm from. Uh, if you are born on a certain day, you get a certain name based on your tribe and your gender. So there's some kind of systematic process in that. I know people from other African countries where they're given a name based on the season they were born in and the order of their birth. So I guess I can't speak for the whole continent with so many countries, but where I come from, we have systematic nomenclature for the first name that a baby has. And then, of course, they add a lot of other names, right? You know how that goes. But yeah, my dad was like, no, he decided we're going to just have one name. So my name theoretically means a girl born on Wednesday, and I am a Fanti tribe. So when other Ghanaians see my name, they're like, oh, this is a girl. They know that for sure from my name. They know what day of the week I was born. They know what tribe I am just by looking at my name, right? Just kind of a little side note here. Did it make nomenclature any easy for me? No. But at some point I'm like, oh, okay, there is some order to this naming, right? Okay, now let's go to non-metals. It's funny when I share this story in class. You should see the students; their eyes kind of perk up. They're looking at me like, "Whoa, what's my name?" And people will be like, "Can you give me a name?" And I'm like, Bob." No, I'm just kidding. I mean, no, they do perk up though, because they didn't realize the systematic name I have. I know. So funny enough, when you go to my country, there's a lot of people with my name because there's a lot of people born on Wednesday who are my tribe. Yeah. So families will normally give the kids other names, but my dad was like, "No, you just get that one name. That's it." Such is life, y'all. Such is life. Okay. So we're essentially done with the ionic compounds. That's pretty much it. You have ionic A's, you have ionic B's, you have, the element and ion, that format. You have element, charge, and ion. Okay, now we have ionic B. I mean, sorry, the molecular compound. With molecular compounds, I'm going to need some more space, y'all. So what I'm going to do here is I'm going to just do a section just for the molecular compound. So imagine this arrow here is extended all the way. I know, I'm sorry. It was supposed to be a nice, neat picture. When I'm on campus, I use the whole board for this part. Okay. Ionic B, generally we have, non-metal. That should be pretty simple, right? But in ionic B, we have two general forms. Okay, we have the regular molecular compound, and then we have the molecular compounds that actually form acids. Okay, so we're going to be studying it this way. Now I'm combining them all together because you guys have a lab where you have to name this way. Now you can Google the answers and not learn the process. And if you're taking other chemistry classes or you go to your job and you're required to know these, then you're stuck Googling forever. When your boss is talking to you the whole time you're on the phone and they're like, why can't you remember any of these, right? I want to teach you how to recall these. Okay, molecular compound. Molecular compound, I told you guys I'm not great at memorizing. So as a student, my question is always, how do I survive? Throughout chemistry, my goal was, I will survive, right? How do I survive this? Growing up, I was used to terms like carbon. So now we're naming molecular compounds, right? Carbon dioxide, we breathe that out. I had learned that biology and learned that, I guess, in life outside of biology. And carbon monoxide, the stuff that comes from cars that kills you, right? So let's use this, how we name this carbon, right? Referring to this, the first element. So that's named as an element. Di, referring to the number 2, number of atoms. And then oxide. The oxygen is not named as an element, it's named as an anion. So I say anion. Carbon dioxide. Okay. Then this one here, carbon monoxide. Oh, now I can't spell. Once again, carbon referring to the first element, and then mon referring to the number of the atoms of the second element. And then oxide, once again, the second element is being named as an anion. So in essence, as we are naming carbon dioxide and carbon monoxide, we are, without really realizing, following the systematic format of naming molecular compounds. Now, let me show you the template. What the template is for molecular compounds is prefix, element, prefix, anion. So the molecular compound, when it's named, generally has 4 parts. Okay? Now let's judge what I just did. Now that we know the rule, let's judge what I just did. Okay, let's see, the element, I recognize the element name here. Wait, looking at this, am I not missing the first prefix? Why didn't I say, oh, I need to say this right here. These prefix here tells you the number of atoms. This is number of atoms, right? So you got a number of atoms, elements, number of atoms, anion. Okay, why did I not say the number of atoms of carbon here? Because the rule is, even though the first prefix is the number of atoms of the first element, you don't write mono, except mono. Mono, okay? So the first prefix, you can use di, tri, tetra, whatever, deca, any of the prefixes except for mono. The mono is somehow left out. Why? I don't know. When they were naming this, I wasn't even born. So I don't know why. This is just what the people decided. Is they decided that they don't want to use mono. Mono will be implied for the first prefix. But for the second prefix, all prefixes can be used. As you can see right here, the monoxide in the oxide was used. It was not implied. Okay, so the mono here is implied. The second part, the mono, is not implied. It is used. Okay. The other thing, did you realize I said monoxide? I did not say monoxide. So we're going to start practicing these rules. Don't worry. Right now, I'm just trying to lay them out. When it comes to the second prefixes here, the second prefix, they consolidate O and O and A and O. So O and O, if you have monoxide, these become, they drop off one of the O, so it becomes monoxide. If you have A and O, for example, pentaoxide, the A drops off and becomes pentoxide. Once again, this is one of those things that you have to kind of learn the rules and practice the rules as we're working on it. Okay. So underneath this is I'm trying to consolidate the rules in one sitting. Y'all have seen how I worked all this out. Once again, as you're watching this later on, feel free to rewind and watch. Okay. We are going to practice a few. Number of atoms, I say here, monoxide becomes monoxide, and then pentaoxide becomes pentoxide. So you're consolidating the A and the O and the O and the O. Okay? Pentoxide, like that. But when you're looking at the name, how do you judge from the name that this is the molecular compound? It usually follows the format prefix, element, prefix, anion. If the name follows that format, then you know. Right? Let me work on this final part here, which is, do I want to do the acids right now? Okay. Before this becomes super overwhelming, let me go ahead and do, because in the lecture, in class, I usually don't actually go through the whole thing like that. I usually do some practice stuff. So let's go back here and practice some element and ion names, right? So for this part, let me detour and go to the lab for this week. I want us to identify ionic A and ionic B before this whole rule learning becomes so overwhelming. I think the lab is posted here. Where is it? Where is the lab? There. Ionic A and ionic B compounds. Okay, I guess this was bouncing. That means it's somewhere in here. Oh, there it is. It should just open. Okay, right there. So hopefully you can see my screen, right? So, while I had this screen here, I just realized that I don't have the periodic table here. So let me look for, excuse me, guys. I need a periodic table. I can't see my key. Periodic table. There. I have my table set up so high. Oh, I need it with I'll just say group number. Group number. So I want the periodic table that shows me group number. Man, the internet these days is like all this stuff, so much stuff. Okay, let me pick one that's not so busy. Oh, I like this one. Is it clear enough? Let's see. Let's see if I can get this to be big. Plus, 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 plus. Oh, it's not clear enough. Okay, well, I just need this on the side of my paper anyway. Where's my paper? Okay, so I need this on the left, and I need this on the right. Somewhere. So what we're going to be doing is trying to identify our metals. So I need the metals right here. And then I need this on the left side here. Okay. So I'm not doing the part where you guys are looking at these chalk, baking soda, wax, and trying to figure out their behavior. I want to look at this here. So I'm not going through all of this. This is kind of summarizing what I'm doing. As you can see, I don't know how complicated mine is, but this is their version and I'm drawing mine. Anyway, here are common ions. Yes, right there. And then we're right here. So I'm not going over this part yet. What I'm trying to do is, oh, right here in the naming compounds. What I'm trying to do here is we learned about ionic A compounds, and we said ionic A compounds. Where is my draw feature? Ionic A compounds. So I'll say IA for ionic A has this format of nomenclature. You write the name of the element first, and then you write the name of the anion second. And that's how we know the element is ionic A. So I'm going back to what I just covered, right? And then we know we have ionic B because ionic B has something extra that the ionic A doesn't have. The element, which is also the metal, we have to include its charge number because apparently there could be more than one, right? So you got to specify the charge so that the person on the other end of the phone does not grab the wrong bottle and then send it all the way from a different country here only to find out you got the wrong chemical. Kind of like something I ordered recently from Amazon, and I was very specific. There was even a picture, and they still got it wrong. Anyway, that's like a whole different conversation. You want to specify the right charge so you can get the right chemical, okay? So what we're going to do right now, I'm not doing the whole lab with you. I just want us to go through, identify what's ionic A, what's ionic B. Remember, ionic A is in the A group, right? Like it's labeled right here. Ionic B is in the B group. So if ionic A, metal, is in the A group, it will have to follow this format of nomenclature. Remember, before I go into this, every chemistry rule has exception. Okay, let's start. First element here in this compound is potassium. Potassium is, I guess I can't click, this is a, what's it called, website. Potassium is right here. Potassium is literally 1A. So this is going to be ionic A, right? I am making that decision based on the position of my metal in the periodic table. Okay, moving on. Copper is my first element here. Copper. I'm looking for C. 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 Ooh, copper right here. So copper is to the left of the zigzag line, right? Copper is ionic B. B. So right here, ionic B. Now, before we continue and get all cozy and stuff with this saying, okay, we got this. Hold on a second. Silver and zinc. Silver and zinc. These are ionic B, but they only have one charge. They are in the family of ionic B, but they just came out that way, having one charge. So for that reason, I want to give you guys exception to the rules, like I told you guys earlier. Silver, where do I write that? Here? Okay. So I should label these exceptions. Exceptions. Sorry guys, I'm writing with my mouse, y'all. I'm trying to use all these tools here. You see why my desktop is crazy? This is why. Exceptions. Silver always has a charge of positive. So even though it's a B metal, we will name it like it's a metal because it's only one charge. When you call somebody and say, hey, can I get some silver chloride? They will never be like, wait, which silver? If they do ask that, tell them, dude, there's only one silver. Okay? Because it's only one silver. So this will always be called just silver, right? So I'll say here, silver has a fixed charge. Silver has a fixed charge, even though it's in ionic B. The other one is zinc. Zinc is always 2 plus. So for that reason, zinc also has a fixed charge. Okay, so what we will do to remember that these two do not really follow the rules of their family members, we will call them ionic B as they should be because they're technically ionic B, but we will put a star star because we're like, yeah, they're a little special. Ionic B, well, I call the star star, but you know, XX. Ionic B XX, ionic B XX. Okay, not done. This is the B group. Other exceptions, when you get to the A group, there's some A groups, right, that are A, but they behave like they're B. The most common one are these elements right here. So you got indium, tin, tellurium, and lead. These four right here. These are the most common ones. Indium, tin, tellurium, and lead. These are ionic A, but they can form more than one charge. So it's like, okay, it's mostly these four, you know. So yeah, you want to be aware of that. But it's not only these four, it's mostly these four. So yeah, they are in ionic A, but we will name them ionic A star star because these are ionic A elements that behave like ionic B, you know, when you're in a certain group but you behave like you're in the other group. Okay, we're not judging them. This is what they do. Okay. Okay, now we can go back here. So let's go back here. Number 3, aluminum. Aluminum is here. So aluminum behaves like aluminum is a fixed charge metal. It's not one of the exceptions. So this is going to be ionic A. We got magnesium. Magnesium is right here. Magnesium is A, no exceptions, right? So magnesium is ionic A. And then Mn, manganese. Manganese is right here. We'll call this ionic B. You see what I'm doing right here? So, because you're still learning this, okay, there's no value in Googling. You want to learn this, okay? So, you want to classify it before you name it. It's okay when we're doing this with chemicals, right? Next one here, sodium. And notice that all of these have just two elements, two elements, two elements, two elements here. Sodium, okay, sodium is what? Right here, ionic A. I'm trying not to go too fast. Potassium, like before, still ionic A. Chromium, right here, not the exception, right? I have my exceptions right here. Ionic A. Zinc, oh, zinc, fixed. Ionic B, star, star, right? Is the exception. Tin, oh, tin. Ionic A, star, star. Yeah, in class, my students are just like, oh, yeah, they like that. the drama, I know, right? So with these ones here, since I have gone through that, I can go ahead and classify these. Okay, so remember, the ones that are ionic A, they'll have the same format of, oh, sorry guys, y'all didn't say anything. Did I just label chromium as ionic A? No, chromium is in the B group. This is ionic B. When I'm going through, I'm always trying to judge what I'm writing because I do sometimes say one thing and write something else. So yeah, this is like chromium is ionic B. Okay, the ones that have similar classifications should have similar format in the names. Remember, ionic A will just have two parts to the name, the element name, the anion name. All ionic A should follow that format, right? Okay, before we get to the molecular compounds, let me deal with this here. Let's try to name a couple, just a couple, of ionic A. Okay, ionic A should have two parts of the name, right? First part should be element name. Second part should be anion name. So I'm going to name a few. Potassium as an element is potassium, right? Potassium. The element name is done. The anion name. The anion is the second symbol or the rest of the symbols, right? Sulfur is right here. Sulfur and anion. But the sulfur has to be named like an anion, not an element. So that will be sulfide. And you guys memorize these from the common ion exam, right? Sulfide. Potassium sulfide. Okay? I'm going to work on 1A number 3, ALN. Al is my first element. I have to name it like an element. So that will be aluminum. Second one has to be named as an anion. N is nitrogen, but as an anion, it is nitrogen. tried. So please notice when I have anions that have just individual elements, the anion, oh, let me see, I'm running out of room. These anion, they call them monoatomic anions because they're made up of one ion, have this following format in the nomenclature. The stem word is the base word that is also seen in the element name, and this one ends with IDE. So the format of nomenclature for the anion is stem-ide. Yo, I was pacing because I did a common ion test too when I took chemistry. It's kind of like a rite of passage. Stem-ide, right? Stem-ide. So stem is nitra, and then IDE is the IDE part that communicates. This is a monoatomic anion. Okay. While I'm here, I'll give you guys this last one. This one here, magnesium, the element. Bromide. The brom is the stem word for bromine, and then I have to name it as an anion. That's what the rule says. So bromide. Okay. You see, the format is systematic. Two names, two names, two names. I won't name the rest of these for right now. I'll come back and talk about that. And then now let's see. This is the opposite. We're given the names and we're asked to write the formula. So for this part here, let's see. Two names. Two names. First one is the name of a metal. Calcium is this right here. Ionic A. Two names, right? First one is the name of a metal. Magnesium. Ionic A. Two names. First one, the name of a metal. Potassium. Ionic A. Two names. First one is the name of a metal, but the metal is zinc. Zinc is in the B portion. Look, it's missing the parentheses in the Roman numbers. This is ionic B that's named like an ionic A, therefore it's an ionic B star star. Next one, two names, right? Kind of like an ionic A, but my metal, silver, is in this area right here. It's in the B. Doesn't the B that have to have three, except for when it's zinc or silver? So this is going to be an ionic B star star, right? Okay, moving on. This is so much easier. This one here, three parts of the name, one part being a Roman number. This is just regular ionic B, nothing special. Two parts of the name, where the first one is sodium in group A, ionic A, metal. Lithium, group A. Once again, you're judging these by the first element, ionic A. Copper 1, come on now. Copper is not the exception, right? And then they put the 1 here, ionic B. Ammonium sulfite, this is one of those ionic compounds. So we'll label this ionic A because it's missing the parentheses, where it's not really a metal. So you can't find ammonium in the periodic table. So you keep going on. Rubidium, like ruby, but element form. Rubidium, Rb, ionic A. Aluminum right here. Also ionic A, not an exception, right? Iron 3, oh, that format, ionic B. No question about it. Sorry, let me stop skipping stuff. Iron 3 is right here, the regular B element, right? Then we have lead 4. So by looking at this first, I can make a judgment lead 4 is ionic B. But let me go find where lead is. Lead is Pb. So this is not lead. This is platinum. This is palladium. Lead is right here. But wait a minute. Isn't lead underneath A? But we said these 4 behave more like B's, right, than they do A. So wait. Don't sleep, iPad. Lead is going to be ionic A star star. Ionic A written like ionic B. And then for this one here, we do have two. This is actually a prefix. So what we're technically seeing here is three parts of the name because this is not, this is, they're written as two names, but this is technically a prefix. Okay. And this one here has four parts to the name. This one here has the word acid. So we haven't learned how to name this just yet. Okay. So you see how from the names, oh yeah, and this is per, so this is not a prefix. Make sure you don't confuse that. You want to recognize the prefix terminology so you know how to name this. Once again, nomenclature is not easy because there's no math. Sometimes students prematurely judge a chapter and say, oh, this chapter is easy, there's no math. No, there's still a system that has to be followed, which is the same thing you do in math, right? So you want to make sure you know how to name the names. If you went through common iron exam and still haven't learned the names, spend the time learning the names, because if you don't, it's going to be harder for you later on because you will still be learning the names when you're having to use the names, which makes things very complicated. Okay. So yeah, let's see. I'm looking at this right now. We have these, as I said, I'm not going to go through all of this. Now, when it comes to naming this, remember you guys learned how to name the common ions, right? The polyatomics. So remember, monoatomics, these are the ones that end with IDE, IDE, IDE. When it comes to polyatomic, like this one's here, you see the quote unquote non-metal part of the formula, it has more than one element or more than one non-metal. You have phosphorus, you have oxygen. So looking at that here, you can say you have polyatomic. Here, you once again, you will have two parts of the name. The first one will be sodium. The second one will be phosphate, because you memorize these, right? Phosphate. Not to be confused from phosphite. Okay? So here's the thing. Just to make sure that this part is not so overwhelming, because I feel like we really need to make sure we got this down. First of all, let me see. What I want to say is I'm not going to finish the nomenclature today because, well, I've kind of run out of time. But not only that, I want to make sure we really got this down, because if I keep talking about this and this is not very clear, then it makes it very confusing. So what I want to do, I know, what is it called? Spring break is next week. I do want to make sure I go through all the nomenclature part of this chapter. So what I want to ask here is this. How do I get back to the presentation? Yeah. So will you guys be able to come in on let's see, tomorrow I have a long day for the class. I have two classes tomorrow, so that will be a long day. Will you guys be available on Friday to finish up the name part? If you won't be available, that's fine. You know, I do have. Okay, great. Then we can go through that way. If you guys have questions, we can go through. As you can see, the nomenclature part is not easy, so we want to make sure we practice some. We can go through, you know, your lab, and then I do have some other worksheets, and we can name some more. Hopefully, so that we can really get this part down. So it's the same time. I don't. Oh snap! I have a meeting at 1 on Friday. Okay, give me a second. So is 11 okay for Friday? 11 o'clock? Okay. Okay, that works. So as usual, I'll send a reminder, and then we can practice the nomenclature to make sure you guys get this part. The more we do, the easier it is on you guys later on. You don't have to work as hard to remember it. Okay? So I will stop here, and then we'll pick this up on Friday. Y'all have a nice day.